Okay, good afternoon. So let us move on further in that coordination compounds. So today it shall be like the lecture number 4. So yesterday we were seeing regarding the isomerism. Okay, there we have seen regarding structural isomerism, in that linkage isomerism, coordinate isomerism, then we have ionization isomerism and hydrate or solvent isomerism. Now in the today's class, let us see regarding geometrical isomerism and one or two examples regarding the optical isomerism and further. Now geometrical isomerism, it's a it's a type of stereoisomerism. So stereoisomerism we learn. So very depending upon the whatever the ligands are there. Okay. So arrangement of the spatial arrangement of the ligands around the central metal atom. Based on that, we have stereoisomerism. It is of two types. In that, one is geometrical, and the other is optical. Geometrical, in that we have cis and trans usually, and in the optical we'll have D and L forms, phase and mer forms, all those are there. Let us see in this geometrical isomerism. Now in the geometrical isomerism, it is basically for the heteroleptic whatever the ligands are there, or the heteroleptic complexes. Heteroleptic means three different kind of ligands will be present, which are bonded with the central metal atom. Say in that, arrangement of ligands is going to be different. Maybe in the square planar, it is in the cis form, it is in the trans form. So one by one, in the geometrical isomerism, let us see. One is square planar complex. Square planar complexes. Square planar complexes of the type. In this we have types. What are those types? First one, it is mx2l2. Okay, it is mx2l2. Now these, whatever the x2l2 is there, so these both are going to be unidentate. Unidentate meaning one pair of electrons are going to be donated. So this will give rise to cis and trans forms. Two forms are there. So those both forms it shall be giving rise to. In this, we have the example of PT, NS3 twice, and Cl2 twice. Both NS3 as well as Cl2, they both are going to be the unidentate ligands. Now in this, okay, how they can be arranged? Platinum at the center, two chlorines one side itself, and two ammonias the other side. Two chlorines one side and two ammonias one side. So this forms a square planar complex like this. So this will be the cis form. This is the cis form of the square planar complex PT NS3 twice, Cl2 twice. And if at all the chlorines and ammonia are in the opposite, if at all the chlorine and ammonia they are in the opposite, chlorine here and chlorine here, and even the NS3 and NS3. So these two, if you take in the opposite, so that time you have the transform, cis form and transform of this PT NS3 twice Cl2, diamine dichloroplatinum. Okay, diamine dichloroplatinum. So this is going to be transform. Why transform means? So these are in the diagonal. Whatever the like type of ligands are there, they're in the opposite diagonals. Even the chlorine opposite diagonal, ammonia opposite diagonal. So cis form and transform. This is one set of example. Next is square planar complex of the type MAPXL. Let's see. Second one. So in this you have this cis and transform. Phase and isomer, phase and meridian form also will come later. So second one, it is MABXL. MABXL. All the four whatever ligands are there, they are going to be different. So this will give rise to actually three different isomers. Three different isomers it will be giving. Then change their positions. So metal atom in the center. You can take all the three. All these three will be isomers to one another. Okay. Now here you take this as A, B, then X and L. So this forms a square planar complex like this. This is one set. Then you change this. You have M here, A here, B you take here, and then this you make it as L. This is you make it as L, X. This is another set. This is another set of the whatever is there, the molecule. Okay, the coordination compound. One more is there. Okay. So here A. So these three places you are changing. Once you kept B and B, L and X. So next time you keep this as X. This is L. This is B. Okay, so these three isomers are possible. If you put it L here, okay, it will be again different. Okay, so that is different, but these three are possible there for the isomers, the three isomers which are existing for this square planar complexes. Okay, one example for this PTNS3. PTNS3. Further, you have NH2OH, hydroxyamine, then NO2 and pyridine, NO2 pyridine. Outside the bracket, you will have again NO2. This can be one example for this. Okay, so MABCD or MABXL. In some books, it is given as MABCD. So there, when it is MABCD also, M at the center and BCD, those three are going to change the places. Okay, then next, coming to the square planar complex of the type MXL2. Okay, MXL2. X and L both are two times. They will be both didentate or bidentate ligand. Here ABXL, all the four are going to be unidentate ligands. Unidentate ligands. In some books, this also I will show it better. In some books, they are given it as MABCD. So that time you have ABCD as it is MABCD. Its next type will be MDBC. This is D, B, and C. Its next is going to be here again as it is A yogurt. This is B, and this will be changed. Exchange. C and D is going to be exchanged. D is going to be here. C is going to be here. Okay. So those three places we are going to change. BCD, BCD, BCD we are going to change, and that will give rise to three isomers. Okay. Right. Fine. Let us go to the next. Didentate. square planar complex of the type MXL2. Square planar complex of the type MXL2. Okay, MXL2. So here XL2, both are going to be the didentate ligands. They are going to be didentate ligands. Example for this, platinum and glycinate. Platinum and glycinate which is didentate ligand shall be the example for this. So didentate wherein two donating pairs are present. So platinum at the center. Now what is glycinate is? Glycinate you have NH2CH2CO, glycinate NH2 CH2 COO. Okay, like this it is. So you can have here NH2, then CH2, then CO and O, and this is bonded here. Another set O, CO, CH2, then you have NH2. Okay, since these two oxygens are on the one side, these two are oxygens are one side, it is called as cis. It is called as cis. In the previous, there was no cis and trans. Okay, or if they give also, they'll give some certain exceptional cases there. The other one, you have NH2, CH2, then CO and O. And here O, next is CO, this is CH2 and NH2. Now here what has happened? The nitrogens and the oxygens are in the trans form. They are in the trans form. This is called as a trans isomer. This is called as a trans isomer. So this type, it is a bidentate ligand. Whatever XL is there, it is bidentate. Bidentate meaning it donates two pairs of electrons. It donates two pairs of electrons, and this is how it can be cis when both oxygens are one side, adjacent side, and it will be trans if the oxygens are in the opposite, or in the nitrogens are also in the opposite. Okay, next is octahedral complex now, MX2L4. Fourth one, octahedral complex, MX2L4. MX2L4 type of the octahedral complex. So which has got two ligands X, and they are oriented in the cis and trans form. Okay, X will be oriented in the cis and trans form. L shall be present in the other whatever the available positions. So it will be an octahedral complex. Example for this: CONH3 4 times Cl2. CONH3 4 times and Cl2. CONH3 4 times and Cl2 over this plus charge. Octahedral means 8 faces. It has got cobalt at the center, like this. if the two chlorines are here and here, if the two chlorines are here and the whatever ammonia is there, four ammonia, they are present here. They are present here. Okay, so this is the square plane, and the two chlorines, when they are just side by side, means of course it's not exactly side by side, this is in the plane, this is in the axial position. When they are nearer in this form, this we call it as the cis. And the other one now, other one, Cl and Cl. Cl and Cl, they are in the axial position. They are, one is above the cobalt, other is below the cobalt, and the remaining four ammonia, as it is like this. NS3, 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 NS3. So this again square at the base, and one above and one below. So this, since it is in the opposite direction, this is called as a trans isomer. Cis isomer and trans. See these compounds, whatever cis or trans or isomers, one form and the other form, they both only the molecular formula is same. Structural arrangement will be different. Properties will be different. Uses also can be different. Okay, uses also are different. Uses need not be the same for this one and this one. They have their own uses. They have their own properties. So this is octahedral complex of the type MX2L4. So here X2 is nothing but chlorine and L4 is nothing but ammonia. Okay, next octahedral complex of the type MX2A2. Next one. Have a look. So the next one is fifth one, octahedral complex of the type MX2A2. X2 and A2. Now here in the MX2 and A2, A is going to be didentate. A is didentate, and you take the X, it is unidentate. In this, okay, X is going to be unidentate and A is going to be didentate. Example for this: CO, Cl2 and En twice, ethylene diamine twice, cobalt dichloride and also ethylene diamine, that is twice. So the name shall be dichloro bis ethylene diamine, cobalt, and the oxidation state. So here in this, what will happen is cobalt is at the center. Cobalt is at the center, and once it will be cis, other time it is going to be trans. So for cis, how it is arranged, you see. This is ethylene diamine. This also is ethylene diamine. And this is chlorine. This is chlorine. Okay. So this is the square plane. At the same time, you have one side, the ethylene diamine to be one side. So that is called as the cis isomer. This is cis isomer. They are adjacent to one another. If they are opposite, then it will be trans isomer. Cobalt, this is chlorine, this also is chlorine. Now here, This is ethylene diamine. This also is ethylene diamine. Now you can see here ethylene diamine, they are in the trans position. Chlorine also in the trans position, in the diagonal position. So this is trans and that is cis. This is trans and that is cis. Ethylene diamine, if it is adjacent, okay, if it is adjacent side by side, it is taken as cis. If it is diagonal, it is taken as a trans. It is taken as a trans. So this is octahedral complex of the type MX2A2. Okay, so where A2 is didentate, X2 is unidentate. You can mention. You can mention that which is which type you can mention and write down. Okay, one more, last. Ma3B3 or Ma3X3. Sixth one, I think. Okay. Sixth one, octahedral complex. Octahedral complex of the type MX3A3. Okay, MX3A3. All these are unidentate only, but this will give rise to, these will give rise to face and meridional or facial and meridional isomerism. We'll see that now. Okay, facial and meridional isomerism. Ma3B3. Example, CONS3 thrice, Cl3 thrice, CONS3 3 times, and Cl3. Okay, fine. So here, how these are going to be arranged? Now all these, whether you take ammonia or chlorine, they both are unidentate only. So let us arrange them. If the chlorine is in one phase, this becomes one phase, and the ammonia is in the other phase. If the ammonia is in the other phase, of course, square at the base, and again you have, so this whatever the portion is there, this becomes something comes like one phase, this is another phase. This is called as facial isomerism. Facial isomerism, facial isomer, we can be saying. And the other one, the position of chlorine, if it changes, the position of chlorine is different. These two, chlorine and ammonia, if they are exchanged, cobalt, chlorine here, chlorine here, chlorine here, and this is ammonia, NS3, this is NS3, also this is NS3. So what this will be then? Okay, so this is going to be meridonian. Mer isomer we call, mer isomer. Meridional isomer. Meridian we say, isn't it? Equatorial, meridian position we say. So that same word here. So if it is in the one phase, if it is in the one phase, it is called as a phase isomer. If it is not in the one phase, if they are in the meridian above and below like that, it is present, and then it is going to be in the meridional isomer. So octahedral complex of the type MX3A3, where both X3A3 both are going to be unidentate. They both are unidentate. Okay, this completes regarding the geometrical isomerism. Let us come to the optical isomerism. Now, optical isomerism arises because of what? Optical isomerism arises because of the mirror images of molecules, but these mirror images cannot be superimposed. These mirror images cannot be superimposed. They are not the same. The atomic groups will not fall on the same point. Such a thing we call it as a non-superimposable. So they shall give rise to something called enantiomers. Okay, enantiomers, and those enantiomers of two types. One is D form, other is L form. Now, what is this D and L form? D and L form is D is dextro-rotatory, L is levo-rotatory. Dextro-rotatory means what? It will turn the plane of polarized light to the right side, and levo-rotatory, it will turn the plane of polarized light to the left side. So dextro-rotatory clockwise also, they say in some books it would have been given as a clockwise. The plane of polarized light is turned towards the clockwise direction, and levo-rotatory, the plane of polarized light is turned towards the counterclockwise or the anti-clockwise. Okay, so these both, they are non-superimposable. Non-superimposable mirror images of isomers, they give rise to optical isomerism. So let us see the example for this. First example, COEN tris. Tris ethylene diamine cobalt. Tris ethylene diamine cobalt. How this will be? Cobalt at the center, and ethylene diamine, since it's going to be a didentate ligand, okay, with two sides it is going to bond with the cobalt. And suppose you have here En, okay, this also is En, this is En, okay, fine, right. So this is one setting. This is one isomer we call. One isomer. Ethylene diamine here, here, here. Okay. So this will be the D form. This will be the D form. Dextro-rotatory, which will turn the plane of polarized light to the right side. Its mirror image. Its mirror image is how? Cobalt at the center. Then you have ethylene diamine, its mirror image means here it will be mirror image. This is another ethylene diamine. This is another ethylene diamine. So what has happened here? These two, they are mirror images of one another. If you take this and put it over this, cobalt will fall over cobalt, but ethylene diamine will not be falling over the ethylene diamine. Only these two ethylene diamines will overlap, and these two remaining, they do not overlap. They give rise to, or they can be seen separately. So this form, it is called as the L form. L form. So what are optical isomers is? Optical isomers are the isomers of the coordination compound here, wherein they give rise to two different forms, D form and L form. These are going to change, going to turn the plane of polarized light towards the right side or towards the left side. D form will turn clockwise or right side, L form will turn counterclockwise or left side. Okay, so these are mirror images of one another, and they are non-superimposable. If you take this and make it fall over that, maybe at the most, if at all, if you turn that, or all the three ethylene diamonds are not going to overlap. They are going to be different. This is this side and this is this side. Okay, so this is one example. Further, next, another example. Another example, let us see. COEN twice, Cl2 twice. Second example, ethylene diamine twice and also Cl2 twice. In this, what will happen? So you have cobalt again at the center, then two chlorines if they are one side only like this. And whatever the didentate ethylene diamine is there, one here and another here. Okay, so this is square at the base, ethylene diamine like this here. So this will be D form. This is D form of the isomer. Then it's whatever the other waveform is there. Cobalt at the center, cobalt at the center. Then chlorine is going to be in the mirror image form. It's mirror image. Chlorine here and here, and ethylene diamine here and here. So if you bond like this, that is going to be another isomer. This is going to be another isomer. Okay, so this will be L form. L form. Okay, so CO En twice, Cl2. So these again, just reminding you, optical isomers. Optical isomers are mirror images of one another. So both those isomers, one if it is turning the plane of polarized light to the right side, the other will turn the plane of polarized light to the left side. Okay, and these both you can see definitely they are not superimposable. Superimposable means now you see these two. You have learnt in the haloalkanes topic. If I hold these two palms like this, they're superimposable. This position is superimposable. So when I hold like this, you are seeing only one hand, and the other hand is just eclipse behind that. Suppose I hold like this. Okay, definitely you are able to make out. I am holding two hands, one behind one, two palms, one behind the other. So these are non-superimposable. These are non-superimposable, we say. These two are different. Okay, like this, it is mirror image. Right hand's mirror images, left hand like. Not all those lines what are there in the palm. Just the image. If you take basically, it is a mirror image. Okay, just have a look. Then we shall move further. Now we'll go to the bonding in coordination compounds. So previously little regarding Werner's theory we have seen. Now let us see regarding the valence bond theory. Valence bond theory. Bonding in coordination compounds. So here valence bond theory. Okay, valence bond theory I've learned in the first year also. So what is that valence bond theory is? Valence electrons and their orbitals take part in the bonding. And if they have the unpaired electrons, so their one unpaired electron in one atom, another unpaired electron in another atom, these orbitals will overlap and that will give rise to a bonding. and that will be a stronger bond. Okay, so basically, and then if at all it is not there, if the available orbitals are not there, so then hybridization occurs. Okay, different kind of hybridization, sp3 dsp2 d2sp3, then such sp3 d2, such hybridization occurs there for making available the space, the orbitals, wherein the ligands can be donating, the ions can be donating the pair of electrons to the central metal atom to form the bond. So that is what is regarding the basic postulates of the valence bond theory. So here ligands are donors of electrons. Ligands are donors of electrons. Metals are acceptors of electrons. So here we can have two types: six ligands which are donating total 12 electrons, or four ligands which are also donating 8 electrons. Two types of complexes we are seeing. In that again we have inner orbital complex and outer orbital complex. Okay, once again, just telling you once again, see, valence bond theory. Valence bond theory, according to this theory, metal atoms or ions, they are going to make available the orbitals for the ligands to donate the electrons in those orbitals. And if at all it is not properly available, so then it will be hybridized in the metal atom. There's going to be hybridization, and that will make available the space for the electrons of the ligands to be occupied in the whatever metals orbitals are there. So depending upon the type of hybridization, the structure, the magnetic property, all that is going to be decided. So here in this NCRT, okay, for the 12th standard, so we are going to learn regarding two different kinds. One is 6 ligand system and other is 4 ligand system. So central metal atom bonded to 6 ligands. Okay, central metal atom bonded to 4 ligands, and that can give rise to two different kinds of complexes. One we call it as the inner orbital complex. One we call it as the inner orbital complex, and the other is the outer orbital complex. Inner orbital complex, outer orbital complex. Now, what is the meaning of inner orbital complex? Now, suppose for a metal atom, okay, suppose for a metal atom, dsp3 hybridization is there. What is the meaning of this dsp3 is the 3d orbital, the 4s orbital, and the 4p orbital in the pattern, in that arrangement itself. First, the 3d, okay, of the metal atom is going to be filled with the electrons, then the 4s is going to be filled, then the 4p is going to be filled. So this way the orbitals are made ready for the ligands to donate the electrons in these are called as the inner orbital complex. First the inside orbital, okay, inside orbital is going to be filled, later the outside orbital shall be filled. So this basically when strong field ligands are coming, means which will bring about the pairing of electrons, that time this kind of hybridization and this kind of inner orbital complex formation is more. And it can be in this type also, sp3d. Now what is the meaning of this sp3 is the sp3d is which are the orbitals that which are involved in the hybridization: 4s orbital, 4p orbital, and 4d orbital. All of the outer only. Okay, 4s, 4p, 4d, all of the outer, or maybe 5s, 5p, 5d. Okay, like this it is involved, let's suppose, then it is called as a outer orbital complex. So this kind of pattern will take place whenever weak field ligands, those ligands which do not make the electrons of the metal atom to be paired. Okay, when something comes, now it's like saying what is a weak field and what is a strong field ligand. A cockroach just comes there. Okay, a cockroach comes there, some are definitely scared, some people are definitely scared, so they do like this immediately. They take their hands and maybe legs close to themselves, okay, themselves of the body, I mean close to their body. So that time For them, even that cockroach is a strong field ligand. Okay, strong field ligand. Snake comes, definitely all are worried. Okay, first initially all are worried. Then maybe one takes that little daring and does something there, and it is being disposed in some manner. Okay, so depending upon the animal, elephant comes. When you see a rat, sometime you are very scared, but if you see an elephant, you are not scared. Okay, if it's a domesticated elephant, because that elephant, remember, it is harmless. So when it is harmless, you do not get feared. When something is very harmful, you get feared. You get paired up, you can say. Your energy, all that energy are pairing it up to make it one there. If at all it attacks, you are also going to attack. In that way, you are going to pair your energy. But something is harmless, you do not pair your energy like that. Okay, you keep as it is. So inner orbital complex for strong ligands, usually, and outer orbital complex for weak field ligands, we say. Weak field ligands will form outer orbital complex. Strong field ligands will form usually inner orbital complex. Now let us take one example and then understand this. CONS3 6 times 2 plus. First example, CONS3 6 times and 2 plus. Now ammonia, it's a strong field ligand. So each ammonia will bring 2 electrons. So like that, total 6 ammonia means 12 electrons are going to arrive from the 6 ammonia. So cobalt should make ready 6 orbitals for the 12 electrons. Let us see. So in order to understand this inner orbital complex, examine cobalt. So let us understand the bonding in this. Oxidation state, if you have to count, x plus 6 into 0 is equal to plus 2. So here the charge is 3 plus. The charge is 3 plus. So this will be 3 plus 3. So cobalt oxidation state, it is plus 3. Means what? It is donating 3 electrons. So first of all, cobalt, the atomic number 27. Okay, after iron is cobalt. So it shall be argon followed by 4s2 3d7. Now, the ground state configuration for cobalt. Okay, so this is the ground state configuration of the cobalt. 3d7 and 4s2. Okay, 4s2. Actually, we have to show this side. We have to show this side. This will be 4s2, 3d7, and 4s2. So when it is cobalt 3 plus, okay, so this was ground state. Ground state. Now let us go for cobalt plus 3. Plus 3 means what? 3 electrons are donated. 3 electrons, 2 electrons from the 4s level, 1 electron from here. So remaining electrons will be 6 now. So those 6 electrons are arranged out. Cobalt 3 plus 1, 2, 3, 4, 5, 6. 4s is empty. This is 3d. And next is P, that's also empty. Now, when 6 ammonias are going to approach, 6 ammonias are going to approach, they are bringing 12 electrons. When 6 ammonias approach, they bring 12 electrons. So for 12 electrons, 6 orbitals should be made ready. So what will happen is, because this ammonia is a strong ligand, these unpaired electrons pair up. First, the unpaired electrons are going to pair up. Okay. When they pair up, and simultaneously there is hybridization. So 1, 2, 3, 4, 5, 6. Then you have 4s level and also the 4p level. 4s, 4p. Okay, this is 3. So when 6 ammonias are approaching, these electrons first they are paired up. After they are paired up, what will happen? These 1, 2, 1, 2, 3, 4, 5, 6. You require 6 orbitals, isn't it? These 6 orbitals are going to get hybridized. So it can be indicated like this. These undergo hybridization. Hybridization meaning mixing. And after mixing, all these orbitals have become of equal energy. These become of equal energy. So 6 orbitals are required for the 12 electrons of the ammonia. Okay, 12 electrons of ammonia. So what shall happen in the next step? Those orbitals of the 6 ammonia shall overlap with these orbitals of the cobalt, and that gives rise to hexamine cobalt 3 plus ion. So when it is overlap, then the next is what? How it appears like. Okay, so now these are going to be occupied by the x what I am writing, each x is 2 electrons. So those electrons are of the ammonia. 6 pairs of electron pairs are being brought from the 6 ammonia. So these electrons are of ammonia. 6 pairs of NS3. Okay, 6 pairs of NS3 electrons, they overlap here. And what is the hybridization? Hybridization, it is D2sp3. So 2 orbitals of the D, that is 3D, 1 orbital of the S, and 3 orbitals of the P3 are going to be involved in the hybridization, later the bond formation. And since it is D2sp3, you have learnt in the chemical bonding lesson in the first year. So this will give rise to what kind of structure? This will give rise to octahedral structure. This gives rise to octahedral structure, D2sp3. And since all electrons are paired, no electrons is singly occupied, so it is diamagnetic in nature. It is diamagnetic and it is octahedral in shape. It is octahedral in shape and diamagnetic. Okay, one more molecule, let us see. Outer orbital complex. So this will give rise to the structure also, let us put it. Then it will be complete. Structure for this. Cobalt at the center. Cobalt at the center. NS3. NS3. This also NS3, also NS3, and then NS3, another NS3. So octahedral structure it shall be. Okay, fine. So regarding this, a 3-mark question can be there. Explain one inner orbital complex of cobalt. Okay, explain the bonding in CONS3 6 times 3 plus. That way it can be, and later comment on the magnetic behavior and the structure they can ask. Because of this hybridization, the structure is octahedral. COF6. Next example, COF6. And the charge over this 3 minus. COF6, 3 minus. When this is there, then again oxidation number first of all. Oxidation number, because you'll require that in the second step. X plus 6 into minus 1 is equal to minus 3. So what will be x then? X will be equal to plus 3. So here also cobalt oxidation is plus 3, but here electrons of the cobalt do not undergo pairing. They'll remain as it is, unpaired. Okay, first of all, cobalt. Cobalt is 27. So argon 4s2 3d7. So when we write, we have to write like this. When you go for the box structure, 4s will come that side. Okay. Now cobalt in the ground state. In the ground state. So it shall be 3d7. 3d7, 4s2, then 4p it is. So 3d7 means 1, 2, 3, 4, 5, 6, and 7. These are 2 electrons. So this is the ground state electronic pattern of cobalt. Now fluorine atom, I told it's a weak field ligand. It does not make, or it does not force the electrons to pair. So what will happen here is these 3 electrons of the okay, we have to come to the first CO3 plus, CO plus 3. That time what is the configuration? So 3 electrons means 2 here and 1 here. So then you have the 5 electrons. This is 3D level. 1, 2, 3, 4, 5. Okay. And 4s is as it is empty. 4p also empty. Then even 4d shall be present, which is empty. Okay. This is 4s, 4p, 4d. Those will be empty. They are not going to be occupied by any electrons. Now here the 5 electrons remain unpaired. They are not going to pair up. They remain unpaired. 4s1 electron I have to show here. This 1 electron I have to show here. 1, 2, and 3. 3 electrons are removed. So remaining 4 as it is unpaired they will remain. So now what will happen is 6 fluorines will approach this. 6 fluorines will bring 12 electrons. Those 12 electrons are occupied where? So once 12 electrons require 6 orbitals. So first orbital, second orbital, third, fourth, fifth, and sixth. Like this, 6 orbitals of the 4s, 4p, 4d are taking part in the hybridization. So it shall be sp3d2. D2sp3, sp3d2, both are different. Okay, sp3d2 means all the outside orbitals only are used up. The inside orbital, though it is there is half filled electrons in the orbital, so they are remaining as it is. They do not get paired because this fluorine is something like elephant. So for elephant, you are not going to get scared. Okay, unless it is a wild. Fine. So here cobalt hexafluoride. So for this, what will happen? So the six fluorines will bring 12 electrons, and those are occupied how? This is 4s level. 4s level. I will not draw this. Okay, or if you want, I'll draw that also. Wait. This is 3D level. 1 electron, 2, 3, 4, 5, 6. 4s level with 2 electrons. These electrons are of the fluorine. So let us represent it as X. 4s level. Then 4p level is there. Here also one more X. Okay, 4p level is 3 orbitals are present. X and X. Okay, then you have 4D. This is 4D. Here also X and X. So now what has happened is before this X electrons of the 6 fluorines are going to occupy the orbitals of cobalt, this will undergo hybridization. Hybridization means mixing of orbitals to give rise to equal energy orbitals, and number of orbitals are also equal. 6 orbitals are hybridizing, 6 new orbitals of equal energy will be obtained. So now this hybridization is what? 1 4s orbital, 3 4p orbitals, and 2 4d orbitals. So it will be sp3d2. sp3d2 means this will also give rise to octahedral geometry. This will also give rise to octahedral geometry. sp3d2. Here, fluorine is a weak field ligand. Since it's a weak field ligand, it will not make these electrons to get paired up. They shall remain as it is, unpaired only. So there is going to be one thing called spectrochemical series. Okay, later in the next class or so, I think I shall be coming to that, wherein we are going to mention the ligands in the order of their field strength, whether they bring about pairing or whether they don't bring about pairing in the metal ions. We are going to learn that. So 6 pairs of fluorine electrons are occupied in this. So sp3d2 octahedral, and since there are unpaired electrons now, since there are unpaired electrons, 4 unpaired electrons are there. This is paramagnetic in nature. This is paramagnetic in nature. Okay. sp3d2 hybridization for COF6 3 minus. Right. So this is an outer orbital complex. Since all the 4s, 4p, 4d, all the outer orbitals are only used up in the bonding, it's an outer orbital complex. Have a look. Then we shall wind up today for this with this. Then in the next class we shall go for the 4 ligands which are going to be bonded. Okay. Have a look.